Usually, when we talk about property-based testing, we talk about pure functions, right? Functions that when you call them twice with the same input, you're going to get the same output back. But very often when we deal with real systems, we might have state, right? We might call into the database or a web server or anything like this. And if you call the same request, send the same request to the server twice, you might get 2 different answers. And so property-based testing in such a context is more difficult, more challenging. Just as useful, but a little bit more difficult to do. So in today's episode of the Haskell Unfolder, we're going to talk about how this is done.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Right, so to have a simple example of a stateful system, I have this hardware board here, this which is shown in the top right here, which is called the FCBTN10 as a MIDI controller. And so obviously I wrote some Haskell code to deal with this thing. And so I can show you what the signals are that I get from this device. And I must mention, this is not the stock device. I have replaced the chip inside here with the EurecaProm chip. I'll put a link in the video description. It just basically means that I get the raw signals from the board rather than any interpretation. It's basically the logic that sits on the board here. It's extremely simple. So if I now press one of these bells, you will see in my console here the signal that I get. I mean, translated into my Haskell library. So if I press the pedal, I'm told pedal 1 got pressed, and if I release it, pedal 1 got released. Right, and if I press pedal 5, we get pedal 5 press, pedal 5 release. Okay, this all makes sense. Now, the more interesting thing happens is when I press more than one pedal at the same time. So if I press 1, and I then press 5, if I now release 5, we would expect to get a signal 5 released, but we don't. Instead, what we get is 1 pressed. And if I now release 1, then I get the release for 1. Similarly, if I first
you never get the release for 5.
I never get the release for 5. Yeah, that's right. If I press 1 and now press 5 and now release 1, I don't get any signal at all. And if I now release 5, I get the 5 release. So this is kind of confusing. And I actually ended up writing some logic that tries to process these things. So if I do, and make some sense of it. So if I press 1, press 5, and now release 5, I get a 5 release, right? Internally, it knows that, oh, 1 and 5 were pressed. I got a message that 1 was pressed, but 1 is already pressed. So it must be that 5 was released instead. Right? So it has some logic in there. And now if I release 1, then I get the expected release. And the other example that I showed you was if I press 1, press 5. If I now release 1, well, I don't get any signal at all, right? So there's nothing that my software can correct here because it is not told anything at all. But now if I release 5, it knows that, oh, that must mean that you release both 1 and 5, right? So we get 2 events at once. Now, to develop this, it's kind of tricky, right? We need to understand exactly what this board is doing. And this is an example of a stateful system, right? I mean, the signals that I get for pressing and releasing 5 depend on what's happening inside the board. And so the goal of this episode here is to come up with a simple model that explains what's happening inside this board and then test that model against what's actually on the board, right? So the goal of this particular case is not to test the board. We know, like, we can't change the board, but it's to come up with a model that explains what the board is doing and then test that the model is right.
Yeah, but perhaps we should say that in general, this is the approach that you take with testing stateful systems, right? You try to come up with some kind of model, and the model serves as the specification. You test the model against the real system. And as is typical for testing, sometimes you discover problems with the model, sometimes you discover problems with the real system, but you try to make them converge, right?
Exactly. Yeah, that's exactly right. Yeah. So typically, the goal is to fix the system to match the model. Sometimes it's the other way around, and sometimes it's both, like Andrew said. In this particular case, we're just adjusting the model. And yes, the goal here, so I started by saying if we send requests to a server, for example, we might get different answers back, right, depending on the state of the server. And so, yeah, exactly like Anders was saying, the goal of the model is to explain at a high level of abstraction what's happening inside the system with a sufficient amount of detail that we can test what the answers are going to be. Okay, so let's start with developing a model that describes what's happening with the FCB 1010 here. it's going to start really quite simple. All we need to know for our model is, again, remember, the model is capturing what's happening inside the board, right? What is the state of the board? And all we need to know for that is which pedals have been pressed. Right? So we can say the model that we're going to use is just a set of pedal. And pedal is defined in my Eureka Prom library, but it's just pedal 1 up to pedal 10, and up and down. But yeah, and all of these pedals here. Actually, I can show you. We don't need that anymore here for now. Okay. Then the initial state of the board is the initial model, right? This is how the board starts out. It's just no pedals are pressed, right? So it's set. Okay, easy enough. Okay, now we need a definition of what happens when we execute actions. So the way that we're going to test stateful systems in general, including today, this is through a library called quickcheck-lockstep, which builds on top of a library called quickcheck-dynamic. But one of the key features is a set of actions that we're going to execute against the system. Right? So if this is a database server, it might be get me that table, update this row, yada, 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 right? In our case, an action is going to be a pedal event, right? Press a pedal or release a pedal. And so we need to say how the model updates given one of these pedal events. And again, pedal event is defined in the library. And so
this is effectively just press a pedal or release a pedal.
That's exactly what it is, yeah. So we are going to get two cases, those two cases, yeah. So we have a press of a pedal. And if then, well, all we need to do is insert that pedal into our set of pressed pedals, right? So simple enough. And if the pedal event is release, well, then you can probably guess, then we're going to delete the pedal again from the set. That's it.
Okay.
Now, our naive... So we have a set of actions that we're going to execute against the system, and those actions are going to give us responses, and that's what we're going to test, right? We never test the internals of the system, right? That's not, don't have access to it, right? We don't check the internals of the database, we don't check the internals of the web server. All we'd ever do in stateful-based testing, at least in this style, is check responses. And so what are the responses here? Well, we're going to have some sort of action. I'm going to press a pedal with my foot, and then we're going to get back a signal from the board that tells us what just happened. Right, that's the output in terms of the to the action. And so our naive model might be, well, no matter what the current state of the board is, the pedal event that we get back as an answer from the board should be the pedal event that we just did. Right, that would be the most obvious thing to do. If I press 5, then the expected pedal event would be press 5, not something else. Right, now we already know that's not true. Right, we already know that this is the case, but this would be the expected model. In fact, when I bought the chip, I thought this is exactly what I would get. So it was a bit of a surprise that I did it.
I mean, you're saying maybe in pedal event because you're already foreseeing that we have these situations where nothing happens. But is it intrinsically clear that you could never get more than one back?
No, that's true. That's fair enough. So this is a choice. Yeah, this is sort of anticipating what I know about the system. That's true. Like the most obvious thing would be this, right? Like we just get the pedal event. And you're right. In general, we could expect that we might get more than one. Yeah, that's true. I'm anticipating a little bit. That's true. Yeah.
Okay.
Okay. Now, there is... Yeah, this is... Maybe I'll come back to this. Okay. We need one more other function which doesn't quite fit in this with this model, but we'll come back to it. So what do we have? Remember, we have a set of actions that we're going to execute against the system. For each action, we have an expected response, right? That's what our naive model tells us, and we're going to compare those responses. Now, the last thing that we need to do is generate actions, right? And the actions that we generate may depend on the current state of the system, right? You could imagine that I can only update a row in a table in a database if I first create a table or something like this, right? So actions are also context sensitive.
You can only release a pedal if you've pressed it before.
Exactly. Yeah, exactly. That's right. It doesn't make any sense to test what happens if I release a pedal without pressing it because it's just physically impossible. Yeah, exactly. So yeah, to capture precisely that, let's find a function called canPerform, which, given the state of the system, given our model, tells us if a particular pedal event is possible, yes or no. And I'm going to call this model old, as in the model prior to pressing the pedal. So we have some sort of event. which is a pedal in a state. Okay, now Anders just mentioned, right, we can't release something that we didn't press. And similarly, we can't press something if we have already pressed it. So we need to check the state of this event. If it's a press, well, then it can't already be pressed. So it can't be a member of the state. And if it's a release, then it must be pressed, right? So it's the opposite. And this would, in principle, be sufficient. I'm going to add one additional constraint here. Easy for human, easier for ETSCO, rather. Which it just helps me that I don't have to cross my feet in all kinds of awkward, twisted ways. So I'm just going to copy this in this definition here. It just makes life a little bit easier for me when actually executing these tests. But in principle, this would not be necessary. Okay. And so then, now we know when we can execute an action. So now we can construct all possible actions. Not possible models, all possible actions given a model. And this is quite simple. What we're going to do is, so this is our model. We're going to we're going to filter for those actions that we can perform in this model. And which actions are we considering? Well, all possible actions. What are all possible actions? Well, we can choose a pedal, any of them. And for each pedal, we have two possibilities, right? We can press that pedal, or we can release that pedal. And that's basically it. Okay. Now, the last function that I was a bit hesitant about is, you noticed when I showed the board, actually, maybe I can show it once more, is that when I press, wait, my editor just disappeared. If I press 1, and then I press 5, and if I now release 1, nothing happens, right? And the way that I think about this in my head is sort of that 5 is masking 1. Higher pedals, higher numbers, that's as a first approximation anyway, mask lower pedals. So you might imagine that in the real system, what's going to happen now, right? We're going to generate a series of actions, then we're going to execute them. What does that mean? Well, it means that the system is going to tell the user, me, to press a pedal. It's then going to look for the signal that it gets from the board, and then compare the signal against the signal that we are expecting to get from the model, right? But if we wait for a signal and there's none coming, we'll be waiting a long time.
Right.
And so it's quite useful for the integration with the real system to know which pedals are even visible at all. So that's the last function that we need. So this is not necessary for the model, but this is necessary for the system on the test. So again, this is again calling this in the model prior to this event. And if no pedals are pressed at all, then the event is visible. Otherwise, it's only visible if the pedal that you're pressing is greater than or equal to the maximum pedal in. I shouldn't have called this event. This is pedal here. They're currently pressed, right? 5 is visible if 4 was pressed, but 5 is not visible if 6 was pressed. Okay, makes sense so far? Okay, good. This is all the code we need to write for the model. Now let's look at what the actual test looked like. Right. So far, this was very simple Haskell code and not really anything specific to any kind of library. Right. So what we're going to look at now is how we integrate this stuff into an actual testing library, so we can actually start running these things. And like I said, this is a library called quickcheck-lockstep. And lockstep refers to that we're going to execute the model and the real system in lockstep. We're going to execute an action against both. We're going to compare the responses. When those responses match, okay, everything is fine. We execute the next one, check again. Next down, check again. So they execute in lockstep. The moment that the responses do not match, we have found a bug, right? Either in the system or in the model. We stop the test and we show you the test case.
Right, and the quick check specific generation comes in for the actions now, right? I mean, so
that's right.
We're randomly generating sequences of actions. Okay.
That's right. We randomly generate sequences of actions. That's correct. Yeah. Okay. So since this is quickcheck-lockstep, which is built on quickcheck dynamic, we're going to see traces of both libraries in the definition here. That's useful sometimes because quickcheck dynamic, the underlying library, is a bit more low level, and sometimes you want to tweak some of the low level details, and you can do so if you wish. But as we'll see, for many of the functions that quickcheck dynamic requires, we can just use functions from quickcheck-lockstep instead. Okay, so the first class is called state model. This comes from quickcheck dynamic, the underlying library. But the model that we're going to give it is lockstep of our own model here. So model is our model, and lockstep comes from the quickcheck-lockstep library. We're going to get lots of complaints about missing instances for a while until we finish all of them. Don't worry too much about that for now. The most important definition that's in this class, in fact, the only definition in this class, is the definition of actions. Right? So we need to say, okay, for this particular test, what is the set of actions? So and this is an associated data type. So it's the action associated with this particular model. And this is a GDT. And the type index here tells us for every action, what is the type of the result of that action? So in our case, we have exactly one kind of action. So this is quite simple. And this is a paddle action. And that it takes a paddle event, like the ones that we saw in the pure model that we just had. And so this is an action in our model. And the result of this is maybe paddle event. And then we need a bunch of functions in this class. All of
this is, I think, perhaps just to briefly say, like, I mean, this is looking perhaps more complicated than is needed because this example is very simple, right?
That's right.
But in general, you could imagine that you are having actions that have completely different parameters than what their responses are, and you need some kind of relation.
Yeah. You might have, I might have, I don't know, act insert row into my database or something, and it might take, I don't know, the identifier for the row, or maybe the contents of the row, and it will give me back, the automatically assigned identifier for that row, or something like this, right? And then different actions would give you completely different responses. Yeah, exactly. Yeah, I chose this example exactly because it is quite simple, and we'll see more examples of why it's simpler than other cases. But yeah, one simplification or simple aspect of this is we have exactly one event, one action, and therefore only one result type as well. Okay. So now we need to define a bunch of functions, and all of these can refer back to functions coming from lockstep. So this is basically boilerplate, except that we need to refer to our definition of what is our initial model, right? Which was the empty set of pedals. No pedals were pressed. All the rest is just boilerplate. Now they can be boilerplate because they require an additional type class, which is called in lockstep. So this is where most of the action happens. Now this also has two associated data types. And they are model values and observable values. So what's that? In principle, when we're testing a stateful system against a model, perhaps the stateful system and a model sometimes give you responses of different types. Right? For example, if the real system gives me a file handle, some Unix socket or anything like this, right? There's no way that the model is going to be able to give you the same thing, right? It doesn't make sense in the pure Haskell model. So maybe the Haskell model will give you back a mock file handle, maybe just a number, right? And so we have some sort of mapping between responses from the real system and responses from the model. That is this model value here. And the type index here is the types returned by the real system. So in our case, we have only one kind of response, which is maybe paddle event here. So we need something here that gives us back a model value in this model for maybe paddle event. And so what's going to be here? Like, what is the model going to return when the system returns maybe a paddle event? Well, this is another aspect of this particular example, is that the model can, in fact, always return the same type. So that makes life easier again, right? So this will be the same, maybe a paddle event. But you could imagine that if this was file handle, for example, then this might be mock file handle. So that's the model values. And then the other associated types is observable values. So sometimes responses from the real system simply should be considered to be unobservable, right? Maybe it's a file handle, maybe it's something that the model just can't respond to or doesn't know about. And so not everything is observable, but we want to compare some parts of the response, but not everything of the response, right? In general. But maybe the model is imprecise. Maybe the model doesn't allow us to give a very precise definition of what we expect. And that should be
it's one of the big opportunities you have, right? I mean, it would be hopeless if you always were like had to aim for a model that describes the complete system faithfully, right? For most real life systems, that's absolutely impossible. So
absolutely, that's exactly right.
It's a big strength that you can pick something that is much simpler and still often find mistakes.
Right. Yeah, exactly. Yeah, totally agree. So that's what the observable values are for. And that's another associated type. And again, this observable of the model. And this A index is the type returned by the real system here. Now in this case, the full event is observable, and this is the only event that we need. So again, this is really very simple. So this looks, as Anders said, more complicated than it needs to be here and here, because we don't require the full generality of the system in this particular example. So one thing we need to tell the system is, how do we observe a response? Like if we get a response of some events, what part of those events is observable? Well, in our case, it's the full thing, right? So this is just an identity function. All it does is wrap it from this to this. Now, the final aspect in which this is simpler than many real systems is that we have no need for variables. So what are variables? Very briefly, is suppose that you have something like open a file handle and then write to the file handle. Right? When we generate a set of actions, how do we generate an action write to a file handle? We would have to generate a file handle, but we can't, right? It doesn't make sense. So instead, you might want to generate an action that says, write to the file handle that you got in the previous action, right? The sort of indirection. Those are called variables, which are often necessary when we deal with stateful systems. However, here we don't use them, we don't need them. And so the only aspect where we'll see this happening is in this function called useVars. So useVars takes an action and is supposed to tell you which variables are used in that action. And that's necessary for shrinking, for example, right? If you generate a set of actions like open a file handle, write to the file handle, if I then throw out open a file handle action, then I can't write to it anymore. Then also the write to the file handle must also be removed. Right? And that's what this useVars is for. But again, we have no variables here, so this is very simple. Okay. So we have a set of actions, we have model values, which are just real values, and we have observable values, which are also just real values. Now we need to tell the system how to actually step the model. How do we execute actions against the model? Well, that's a function called ModelNextState. It takes an action. In this case, this is just one action. It takes a context, which tells you the value for all variables. Since we don't have any variables, we don't need to worry about this. And we get a model. And then we need to return two things here. Can I see what the things are that we need to return after all the... Yes, here. We need to update the model, right? We need to, the second value here is the updated model. And we need to give us the response from this action. Did I already define the responses? Oh, no. Oh yeah, that was this naive thing here. So the updated model is this, right? That's the update function that we wrote. And then I'm going to call our naive function, which is the naive guess what the answer should be, applied to the action and then the model itself. And then the other thing that we need to do is we need to say, how do we generate arbitrary actions? And again, we get the context, which again, we don't need. So what we're going to do is we are just going to use the quickcheck elements function, this standard quickcheck that picks a random element from a list of elements.
And so what's the possible, what did you call it? Possible actions?
That's right, possible actions here, yeah. except that this is not quite what we want because they need to be wrapped in action. But action is a GDT that has a type index. And so we also need to wrap it in a constructor that hides that type variable, because we might want to pick, an action that would, irrespective of its return value. So yes, so we're going to map some action petal over the possible actions in this state. Okay. All right. Yeah, that's where missing instances. We'll fix this in a second.
Okay. Yeah.
We're nearly there. We have defined the model. We have defined the actions. We have set how the model changes over time when we execute actions, and we have generated how we generate arbitrary actions. The last thing to do is to connect this to the real system. How do we actually execute these actions against the real system? And again, this is in two classes. Like before, we have run model coming from quickcheck dynamic in our lockstep in our model. And this system monad here is the monad that runs the real system. This is, I have a module here called SUT. That like talks to the actual FCB 1010, right? I won't be showing you how that works, but the details are in the repo if you're interested. Link in the video description. But it's basically, open the MIDI port, all this kind of stuff, right? All the low-level technical details there. So this defines.
But this is something that you wrote for the purpose of this thing, right? I mean, it's not part of the testing framework or anything. It's
no.
Something which is specific auxiliary code for the specific domain.
So this system monad is a reader over a MIDI port, that sort of thing. Yeah, so stuff that I wrote. Yeah. And again, we have some boilerplate here that we don't need to worry about. The real function that we do need to worry about is how do we perform an action, and again, we have a context here also, against the real system. And what we're going to do, in this case, performing an action means telling me what to do, right? So I'm going to show the instruction to the user. And then if this pedal is visible, given the current state of the system, so it's quite useful actually that we get the model as an argument here. Well, then we're going to wait for the event. Otherwise, the only thing we can do is just delay a little bit, tell the user, okay, just please execute this action, and then we'll wait, and hopefully you've done what you needed to do, and then we'll, we don't return an action here, right? The model doesn't return anything. It would be nice, by the way, if you could just thread delay here, rather than having to predict if this is visible, yes or no, and then just timeout. That doesn't work, and I think that doesn't work because of this is a low-level C function that blocks, and so they cannot be interrupted. We actually have an episode about this. Yeah. So that would be nice to fix, but that would involve fixing the C code to block in a different way, which might be complicated. Okay, nearly there. One more function. Remember that we had this observable thing, right? And we said for the model, it was basically just the identity. We need to do the same thing for the real system also. But again, it's just as simple here. Observe real in this case. So we get some response, and we just need to wrap it in the event. That's it. Now, hopefully, once I add some show and eq instances, all the type errors disappear, and they do. Okay. Actions
just a random side remark. So typically, I mean, you're when you're talking about quickcheck, you're always very emphasize the importance of shrinking, but you've deliberately left that out here, right? I mean, it's because of the it doesn't make sense because you're involved, right?
Yeah, I mean, think about what shrinking does, right? We're going to generate arbitrary actions. We're going to execute them. Executing means telling Haskell what to do: press pedal 1, release pedal 1, etc. Right? And then we're going to, if it were to shrink, the way that would work would be throw out random actions from this list as long as we can, right?
No, then tell Haskell to do it again.
And that is a lot of work, right? So in this particular case, not shrinking is actually much faster because you can look at the test case you know how far it was successful, and then when it wasn't successful, and then just look at it and see if you can figure it out. Yeah, of course, in most cases, running a test does not involve a human actually pressing some buttons. At least I hope not. So in that case, shrinking was much more important. Yeah. That's right. Okay, so when I'm just going to paste in a main function here, which is a little bit detailed, but hopefully not too difficult if I just quickly run through this. So this is a Tasty test suite. We have some ingredients. Ingredients are just a way to configure Tasty, and one of the things that we need to do here is add a command line option so I can specify a MIDI port. Okay, fine. That's what this guy is. Then we get that action. Then we disable shrinking for precisely the reason that we discussed. And then we also just do a few tests. We don't need the hundreds of tests because, again, I have to press all the buttons. And then we have one property, which is test property. So test property is coming from the library. Sorry.
From Tasty.
This is coming from Tasty, yeah. And then run actions is coming from the library, yeah. And so it needs to be told which model, how to initialize the system and terminate the system for every test, and then how to execute this model. Like, remember, we had the system mode here, which was just run reader T, right? It's a reader T. So we need to say, how do we get this thing in I/O? That's what this last argument is, and that's it.
Okay. So
we should now be able to test this. So let's see if that's actually. Oops. Ooh, wait, what's happening? Huh?
Weird.
That is very weird. Maybe I didn't save it. Maybe that's what it was.
You still had the empty main, then yeah.
Yeah. Okay, good.
Yeah.
Okay, that's reassuring. Okay, so I need to give it a MIDI port. Okay, so it tells me press pedal 4. Okay, I can do this, and now it tells me press pedal 1. Okay, I can do that.
You should probably show the board.
Yeah, it's already it already failed. Right, and that makes sense, right? Because the board does not respond when I press pedal 2 when pedal 4 is pressed, right? Because pedal 4 masks
pedal 2, and
we can see
that from the output.
Yeah. So we can first see this is the test that it generated. So a whole bunch of pedals, and we only got through the first 2 before we got an error. So we didn't actually have to execute all of them. And it told us that the first one was fine. And then the state after that was pedal 4. Okay, that makes sense, right? Pedal 4, the response was correct. And then the current state of the board was pedal 4 is now pressed. And then after the second one, the state of the board is pedal 2 and pedal 4 are pressed. And now we can see a divergence, right? The real system did not return anything. Yeah, and the model told us, well, actually, we expect to be told that we pressed pedal 2. Okay. So let me just copy in the non-naive model. And the details here are not all that interesting, but it's basically a release is never visible unless there's nothing else pressed. And if I do release something, a release is never visible as a release. If I have 1 pressed, I press 5, I release 5, what I'm going to be told is that 1 is still pressed. That's the signal I get. I don't get told 5 was released, I get told 1 is still pressed. So that's exactly what this is saying. Like if I press something and this is masked by something, well, then I don't expect to see anything at all. Otherwise, I get the event that I expect. If I release something, if no other signals as pedals are pressed, this is the only pedal, then I get the release that I expect. Otherwise, if it's masked by something, again, I don't see anything at all. And finally, if there's anything else pressed, but it's smaller than what I just released, I'm going to get a press event rather than a release event for that other thing. Right, so this is...
So there's one question that just comes to my mind, which like perhaps you've hidden in the easy for human, I don't know, but because like how do you prevent 3, like that there is something like that tells you to press 3 or 4 pedals at the same time?
Yeah, that's also in my easy for human test. Yeah.
Okay.
Yeah. So that's a fair question. Normally, I guess you would have had to add that to this because in particular, I don't think it matters for this particular test actually, although it would be very difficult to actually execute it. I only have 2 feet, so if it comes.
I mean, and probably the system does have some well-defined behavior even in that setting. It's just difficult to actually. Yeah.
Yeah. However, I think my logic that corrects the signals does assume that you don't press more than 2 signals. So then, and I think it's a necessary assumption.
Okay.
Anyway, let me just replace this naive now by this thing emitted. What is the emitted signal? And now we should just be able to run this again. And I guess I could show the board again. Okay, so it tells me
makes it more believable that you're really doing. Yeah.
You don't trust me. That's totally fair. I got press pedal 2. We get the same one. Okay. I now need told to release pedal 2. Okay, fine. I press 1. No, and so forth. Right. So it tells me to release 1. Okay. Now it tells me to release 4. If I don't mess up, like the model is now correct, right? So we'll have like I don't know how many actions there were, like maybe 20 actions in this thing, right? Or 14, whatever. Ultimately, it will tell us, okay, the test succeeded, and will tell us. If I mess up, right? Maybe I press 5 or maybe press 2, whatever. Maybe I press no. Let me press 5. It's a bit more difficult. Then it tells me to release all pedals because it found a bug, right? We were expecting a release of 4, but we got that 5 was pressed. After all of these state changes, which were all correct.
Yeah, so basically it complains immediately, and that tells you implicitly that, like in all the steps before, you did not find any mismatches.
That's right. Are there any other questions?
No.
This is basically all I wanted to show.
I think everybody is just happy.
Okay.
Yeah, so thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And as usual, feel free to leave further comments under the video. And we'll be back in a couple of weeks as usual. Thank you very much.